Okay, so as advertised, we are ultimately going to take this unit on partial derivatives into multivariate optimization. Okay, so this is going to be a multi-parter, probably two parts to get us there. This part is going to focus in on what's called the directional derivative and the gradient. We're going to define a directional derivative as being, so if I have a function f of x, y, that's differentiable at some point x null, y null, and then I have a unit vector AB, so u is going to be the vector AB, it's going to be in R2, and u is a unit vector, so its magnitude is 1. So if I do that, then I'm going to get this thing where I'm going to say it's the derivative with respect to u of f x null, y null is going to be the limit as h approaches 0. And what we're going to do is we're going to move a little bit here, right? So we're going to move off of x null a little bit toward a. So that's h times a. And we're going to move it a little bit in the y direction toward b, h times b. And then we're going to subtract where we were originally. So x null, f of x null, y null from that. And that's all over h. Okay, so it follows the classic formulation of a derivative, except for we're moving both the x and the y, and we're letting this vector AB determine where we're going. So if this is the case, we call this the directional derivative at x null, y null in the direction of u, the vector u. So if you kind of think about what's going on here, we are kind of at this point x null, y null in the floor. We're moving in some direction given by vector u. And above this, on the surface, we're asking the question, what is the rate of change on the surface in height as I'm moving in the direction of u? Is it going up? Is it going down? What's happening to the height as I move in that u direction? Now the problem with this definition is it's not very computational. So we're going to pose a computational derivative and then show that they are actually going to get the same thing. Okay, so the argument is that the computational formulation here is d of the u vector of f at x, y should be the partial with respect to x of f at x, y times a plus the partial with respect to y at x, y times b. Okay, so why does this work? So let's prove something here. So we're going to start by letting g of h, so g is going to be a function of h, be this little piece of the derivative that we were working with. So this is the f of x null plus ha, y null plus hb. So this means that g prime of 0 should be the limit, right, as h approaches 0 of g of h minus g of 0 over h, which should be the limit as h approaches 0 of f of x null plus ha y null plus hb minus f of x null y null all over h, which is the directional derivative. Okay, so that's f of x null y null, right? Okay. Because you throw 0 in here for h, and this is going to come out with this guy, right? Because, all right, so we got that. So that's the directional derivative. So now we're going to start building from the other side. So we have that g prime of 0. If we define g as this, gives me the directional derivative. Okay, so let's hold on to that and start building. Okay, so we know this. We know that x, so let's x, we can like kind of build a set of parametrics here. X is x null plus HA. We're going to let y be x null. Sorry, that should be y null plus HB, right? So this is like two parametrics here. Okay, so if we use the chain rule, this is what we did last class for g prime of h, right? This is going to give me the partial with respect to x at xy, right? And that's going to be times a plus the partial at xy times b. Okay, because this is the partial of f there, and we get the a, get the b. So if I let h go to 0, right? So if I let h go to 0, then f of xy is going to f of x null, y null, right? So that's going to happen. And let's see, if I work g prime of 0, right? G prime of 0 should be f of x null, y null, because I'm going toward 0, right? Times a plus f of y x null, y null times b, okay? Which, since g prime of 0 is the partial derivative of u of f of x null, y null, that means that's equal to f sub x of x null, y null at a plus f of y x null, y null at b, which is, there we go, we've proven what we've set out to prove, this, that the partial derivative is this computational reality. A quick side note here, you can also kind of make this polar, which helps in certain situations. Instead of u being AB, we could visualize u as cosine theta sine theta, right? And we're going to just wrap this all around a theta variable. So in that case, the derivative on u of f should be fx at xy cosine theta plus fy xy at sine theta. So we're going to kind of tuck that one away a little bit as an alternate formula. But that one will come up if we try to envision stuff as polars, right? So let's take an example of working a directional. Okay, so we're going to work an example here. Let's say that we have the function f of xy, and that's x cubed minus 3xy plus 4y squared. What we want to do is we want to let u, so we're going to kind of work this in a polar way. U is going to be the vector that makes a is going to be the vector where theta is pi over 6, right? So, and we're going to kind of measure this thing. So we're going to try to find the directional vector from the point 1, 2. Right? So let's kind of work this out. F sub x of xy is going to be 3x squared minus 3y. Right? So that partial at 1, 2 ends up being 3 minus 6, which is negative 3. fy at xy is negative 3x plus 8y, right? So fy at 1, 2 is going to be negative 3 plus 16, which is just going to be 13. Okay, so let's see. The cosine at pi over 6 is root 3 over 2. The sine at pi over 6 is 1/2. So this directional derivative of f at 1, 2 should be the f sub x, which is negative 3, times cosine theta, which is root 3 over 2, plus, let's see, this is going to be 13 over 2, because it's going to be 13 times 1/2, which gives me like negative 3 root 3 plus 13 over 2, which is approximately 3.9. So if I move in the theta is pi over 6 direction, then I am increasing at a rate of 3.9. So we're going to even make this a little bit easier to visualize computationally by introducing something we're going to call a gradient. Okay, so let's define the gradient here. The gradient is defined as, so we gotta let f of xy be differentiable. And if that's the case, then we're gonna get this function del f xy. And that's gonna be the, it's gonna be a vector where the first item in the vector is, the component of the vector is the x partial at that point, and the second component in the vector is going to be the y partial at that point. Now this could be scaled up, like this doesn't only have to be two-dimensional. You can have an f, x, y, z, or x1, y1, or x1, x2, x3, x4, xn, but for our own purposes we're going to work with a two-dimensional gradient. So this is what we call the gradient. So if you follow here, then the directional derivative at xy is actually the gradient at xy dotted with u. So that actually kind of makes this a little bit simpler to carry around with. So let's work with an example of this, and then we'll kind of pull an important theorem. Okay, so let's take an example. Let's say that f of xy is sine of x plus e to the xy, and I want to find the gradient of f at the point 0, 1. So I take fx at xy. Right, so that's going to give me cosine x plus y e to the xy, and fx at 0, 1 is the cosine of 0 plus 1 times e to the 0, which is 1 plus 1, or 2. Okay, and fy at xy comes out as, well, that just goes away, so I'm going to get an x e to the xy, and fy at 0, 1. Well, the x is 0, so that's 0 e to the 0, which is 0. So the gradient of f of 0, 1 works out to be 2, 0. So it's just the vector 2, 0. All right, so how does this lead us toward optimization? All right, so we're going to get a theorem here, and it's going to seem kind of odd, but we're going to say that the maximum value, if u is in R2 and u is a unit vector, right? So the maximum value of the directional derivative for u at the point xy is equal to the magnitude of the gradient at that point. And this occurs when u and the gradient of xy are pointing in the same direction. So this seems kind of outlandish. One is that the maximum value for the derivative is the magnitude of the gradient, and even better, it happens when the gradient has the same direction as the u in the directional derivative. Okay, so if this is the case, then we have found some semblance of optimization here. That is not an intuitive reality, so we should have to prove this. So right off the bat in the proof, we know that the directional derivative is equal to the gradient times the unit dot with the unit vector, right? So it's gradient dot unit vector. Okay, so let's think. Law of cosine says I can break that apart. So that's going to be the gradient magnitude times the magnitude of u times the cosine of theta, which is the angle between the gradient and the directional vector. Now, the nice thing about u is that it is a unit vector, so that magnitude is going to be 1, which means that that goes away. Okay, and here's the nice neat little part. When is this maximized, right? Well, this is going to be maximized when cosine of theta is equal to 1, right? So when does cosine of theta equal 1? Well, this happens when theta is 0 or some multiple of 2 pi. Well, what happens when theta is 0 or a multiple of 2 pi? Well, that means that this thing, the angle between the gradient and the directional vector, is 0, which would imply that the directional vector and the gradient have the same direction. So we now have that the maximum happens when the directional vector and the gradient have the same direction. Okay, so and if you follow that, this happens when the cosine is 1. So when that happens, that goes to 1, which means the directional derivative is in fact equal to the magnitude of, so the maximum of this, right, of the directional derivative is when this happens to be equal to that, because the cosine just goes to 1, and now we have proof. So short little posted card proof, somewhat elegant, but it makes its point. So let's see if we can use this to find some sort of maximum. Okay, so f of xy, let's let that equal, so we're going to do an example here. F of xy is equal to x e to the y, right? And I am currently standing at 2, 0. So I want to know what direction do I have to head in from 2, 0 to go upward as fast as I can. All right, so the argument here is I need the gradient, right, at 2, 0. So if I take the gradient at 2, 0, I get fx xy. So this is going to be, let's see, that's just going to be e to the y. So fx at 2, 0 is going to be e to the 0 or 1. Okay, so fy at xy is, well, that's just going to be, again, x e to the y, right? So fy at 2, 0 becomes 2 times e to the 0, which is just 2. So this means that the gradient of f at 2, 0 is the vector 1, 2, right? So if I take the magnitude of that, right, it takes the magnitude of 1, 2, right? That's the square root of 1 squared plus 2 squared, which is the square root of 5. So that is the maximum value for the directional derivative. And so this is the max for the directional derivative of f of 2, 0, which is root 5. And in what direction is that happening? It happens in the direction 1, 2, because that's the direction of the gradient at 2, 0. Hence, that's why it's called the gradient. But usually we give that as a unit vector, so we're going to divide that by the magnitude. So it's going to be 1 over root 5. 2 over root 5 is the unit vector that gives the direction of the maximal value of the directional derivative. So if you kind of think about this as our hill climber going to work, if I want to get higher on the hill, I go in the direction that the gradient tells me. So I keep following the gradient up until the gradient becomes 0, and then I can't go up anymore, which means I'm at a local maximum and I'm at the top of the hill. So once I find all the local maximums, I'm just going to go and compare them all and say, hey, that's the absolute maximum. And I'll have the solution to an optimization problem, which is where we're heading in the next lesson.